computer. Okay, so we're starting today, and it's a very interesting topic, how to make a machine learning model smaller. And this is me, and well, I am now CTO of BixBeta, which is a startup, which is not really related to machine learning, but we still hope to do more of it. Anyway, so model as a compressed representation of data. So on this picture, we see a lot of points, and our model is just to draw a straight line so that for a given x, we can predict y, right? So our model is simply ax plus b. It's a straight line. A is a slope, b is an intercept, and it's a very simple model, right? So we start with hundreds of xy points, and our goal is to be able to predict y from x. So given x, we want to predict y. So if we don't have the model, then our approach would be, okay, we have x, we find some points, these blue points around this x, we look at the y values and we calculate average y, and this will be our prediction. But to calculate things this way, you have to keep all the original data, and you have to search for these points which are in close vicinity, and then you have to do calculations. So it's complicated. Whereas if you have a model, like a simple ax plus b straight line, then it's very simple, and calculation is really, really fast. So it's a good thing. Model is a good thing. So we're compressing our knowledge about the data using the model. Okay, there is a term Occam learning. So Occam learning is a model of algorithmic learning where the objective of the learner is to output a succinct representation of received training data. Again, data compression. Occam learning is closely related to probably approximately correct learning, PAC learning. Occam learning is named after Occam razor, which is a principle stating that, given all the other things being equal, a short explanation for observed data should be favored over a lengthy explanation. And parsimony, extreme unwillingness to spend money or use resources. So parsimony implies predictive power. It's good to be lazy, it's good to be simple, right? So this lecture is all about that. Well, this slide I like to show because it shows, like, if you have some points, you can have a good model here in the middle, but maybe you use model which is too simple, then it is biased, right? It doesn't follow the data close enough, or you overfit. So you close it into many details, but then of course, if you take another data set, the noise will be different. And so what happens if you overfit the error on the test data set, instead of going down, actually goes up, right? So on the training, it always goes down, 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 down. But if you have another data set to validate, what happens at first goes down, but then it goes up. So that means that somewhere here you need to stop, right? So this is a pretty famous, not famous, but like way of thinking. And you need model to be simple, but not too simple, right? This is too simple. This is high bias, underfitting. And this is high variance. It's too sensitive to individual data, so it's overfitting. So the truth is compromise in the middle. So trade-off. Okay. So here we're talking about L1 and L2 and what is called norm. So the idea is, okay, let's say you're calculating a linear regression. So you have y values and you try to model them using sum of some x's with some coefficients beta. So it's a linear regression, right? And this sum is an error. And if you try to find beta coefficients to minimize the error, so suppose this dot here or here, like whatever, this will be the point of minimum, right? But you also don't want these coefficients beta to be too big for whatever reason. And you can add another term here which will sum absolute values of betas or will sum squares of these betas. And now instead of minimizing just the error, you minimize error plus this thing. So the sum of betas, it's represented like absolute values here as this square, and here for sum of beta squares. So sum of absolute values is called L1 norm because this is like the first power, and beta 2, like 2 is second power, that's called L2. And so what you want to find combinations of betas. In this case it's two-dimensional, so it's beta 1 and beta 2, where it touches this guy. So this will be a minimization of this expression. Or for L2 norm, it will be this point, right? So what's interesting about using L1, that the point where it touches is usually at the, like what is called vertex, like at the angle. So where one, like beta is 0 and another is 1. Well, not 1, but whatever value is. So if you're using L1 norm and you minimize this, you end up with a solution where some beta coefficients will be simply 0. And this is called sparse. So if you're looking for a simpler model, smaller model, you may like to use L1 norm because you will get a model with less parameters in it. So it's a sparse thing. So lasso is least absolute shrinkage and selection operator, and lasso favors sparse solutions. So L1 norm is lasso. So ridge regression, we add regularization with L2 norm. So this is ridge regression. And with absolute values, it's lasso, it's L1 norm. Okay. This is the same thing, just reintroduce again. So L1 is sum of absolute values, L2 sum of squares. And this, okay, this is lasso 1, this is P2. This what will happen for P4, and this is P like square root, right? Whatever, you can be creative with how you construct your error function. Anyway, so one way of simplifying and making the model smaller is to use L1 instead of L2. Okay. How reduce memory used by random forest? So mostly in the next several slides, I'll be talking about boosting, but first I'll start with random forest. And the simple thing to do is to reduce the depth of the trees. Just to remind you, random forest machine learning model, the solution is presented as a set of trees. And it may be 100 trees or 200 trees or 50 trees. So you can vary the number of trees, you can vary the depth of trees. So there are some parameters which you preset before you train the model. And well, it's obvious, if you reduce the number of trees, the model will be smaller, right? If you reduce the depth of trees, the model will be smaller. So here we go through some depths and okay, so output. So by default, mean depth is 42 and single tree size is 0.5 megabyte, right? And that for a single tree, and for a total with probably 100 trees, the n estimators is 100 trees, we get about 50 megabytes. But then if we reduce the depth to 6, right, so the model becomes shallow, and the way to do it is just define it as like random forest classifier max depth equals 6. You just provide this argument. Then suddenly you see that size of the tree goes down like 50 times, and overall model size goes down again more than 50 times. So easy, right? And what's interesting is that actually, well, I don't show it here, but the error also went down a little bit. So having deeper trees doesn't necessarily help to make model more accurate. You have to test those things. So you can have model which is smaller and at the same time more accurate. Okay, Here we're talking about XGBoost. Usually I start with random forest when I approach some problem, but then I switch to boosting algorithm for production. Boosting can handle nulls properly. Boosting it has well, it may reduce error. It's a good thing. So boosting is actually better than random forest, and I always switch from random forest to boosting algorithm. And there are different parameters. There are different variations of boosting algorithms. So for example, for XGBoost, we can reduce number of trees, we can reduce depth of the trees, we can increase learning rate, we can use feature selection methods, right? And again, using something like lasso regularization, we can select only important features and remove some others, so get a sparse solution. We can use smaller data types. For example, instead of using default float 64, we can go to float 32 or even like smaller float. And at the end, we can compress the model file, right? So, but as you do it, as you make a smaller model, of course, you need to test the quality, the accuracy of the model, right? Okay, let's do some stuff here. So this is some code where I generate the data, train the model using XGBoost regressor. So given this data which was generated here, right? Estimate the error, and then dump the model into a file, and OS path get size, right? And this gives me the size in, I think, in kilobytes. Okay, and then I tried a different set of parameters. Number of estimators is 50 instead of 100, right? Max depth is only 3 instead of the default. I'm not sure what the default was. But anyway, learning rate and random state, well, random state is always 42. Anyway, so we have this reduced model, we run it, we calculate the error and so on. And then we also, when we save it as pickle, and we can also gzip it, right? So, and then we print the final table. This is part of the final table. So this is original, reduced, and compressed. So we managed to go from a size of half a megabyte down to 12 kilobytes. So this is really impressive, right? The error increased a little bit. So the R squared, because this is regression, I guess, went a little bit down, but the model drastically smaller. So you have to make a decision, like maybe you shouldn't compress it that much, maybe if accuracy is important for you. But anyway, hyperparameter tuning. So what you can do some sort of search in the space of hyperparameters to select the best set. Like, for example, maximum depth, learning rate, subsample. So there are 3 hyperparameters here. And we go through all of them in loop. And for this, our favorite scikit-learn has something called grid search. And we just give it the model and the parameter grid, and it goes through all these parameters and it finds the best thing for you, right? So this is grid search. Another is randomized search. Doing similar thing, I just provide the code, so how easy it is to find a model which will have a smaller size, right? Or accuracy, whatever. In this case, I estimate accuracy, but we can also go for the size. Bayesian optimization. Well, if you have, let's say you just have 2 parameters you optimize on a plane, and you need to find a point on the plane. So you start going and you see, okay, if I go in this direction, it's better. Then I continue going in this direction, and you select where you go depending of your previous experience, right? It's kind of like gradient search. So if you have just few parameters, you can use grid search, right? And it will finish in reasonable time. But if you have many parameters to optimize, you have multidimensional space, then grid search can take a lot of time. So in this case, it's better to kind of use some logic where you're going. If you know that this direction you go, it gets worse, so you should not go there, right? You should only go in like good directions. So there is a module called hyper-optimization for Bayesian optimization. This is the link where I took it from, and whatever, this is example. So you see, it's not difficult to improve your model. It actually takes, I don't know, just a few minutes. Okay, now, before I was talking mostly about classifier. Yeah, you see XGB classifier model, but a similar approach can be used for regressor, right? XGBoost regressor. So this is example of code where we create a regressor. We create a parameter grid, 1, 2, 3, 4, 5, 6 different parameters, and each one we have like 3 different values. Wow. So imagine if you multiply 3 times 3 times 3, like that is a lot of parameters. So here we do a grid search, which is not optimal. Probably we better do Bayesian search, but anyway. But it goes through all this, lots of output, and it finds like the best set of parameters, right? And then given this best set, we evaluate the model. Okay, what we also can do, when we evaluate the error, we can create our own function. For example, we want a compromise between the accuracy and model size, or something like that. So we can create our own estimator function, which will create some custom score, which we came up with. And then we use make scorer from scikit-learn metrics, which will create a scorer. And then when we do grid search, we pass it the model, and we pass it this custom scorer. And yeah, so I wanted to put more code just to show the real example. It's not that difficult, but I think it's already too much code. Okay, size reduction, XGBoost, CatBoost, LightGBM. So XGBoost is a very famous model. Everybody's using it. CatBoost coming from Yandex, from Russia, search engine, and yeah, it's very good. And LightGBM comes from Microsoft. The benefit of CatBoost is that it's very powerful, and it treats categorical variables well. And it can easily treat thousands of features at the same time. So they all have their pluses and minuses and areas where they should be applied. And this is, so what I actually did, I ran the code and compared them. And this is the notebook on my GitHub, which demonstrates how it works. But let's look at the results. First of all, let's look at a mean square error. And you see that the best precision we get from CatBoost, right? So it's a really good fit. And we were able here to change parameters to go from, what is a kilobyte? So it's about megabyte size down to 63 kilobytes, which is good. And at the same time, the error is still very, very small. Well, in comparison, this is XGBoost, right? It was smaller to start with, and it's even smaller in compressed format. The error, well, it's good. It's actually not bad at all. It's so maybe you will go with XGBoost if you don't care about the difference between this and this. And XGBoost always trains faster. So maybe you will choose XGBoost. Or LightGBM, again, it's not bad. We go down in size, and we have a reasonably good accuracy. So here are some links where you can read some more data about this. Okay, talking about data centers, which consume kilowatts of energy to make whatever decisions, modern chat GPTs or whatever, using this NVIDIA DPX H100s. And the brain consumes only 12 to 25 watts. So yes, we want to somehow make models simpler and take less energy. These are old, I don't remember, this is maybe 4 years old. This graph showing like the trajectory, like how convolutional neural networks were becoming bigger and better. So you going from just few megabytes to 155 megabytes. Of course, by today's standards, it's nothing, right? When you have 175, or with new NVIDIA, it's like more than 500 billion parameters. But anyway, so models tend to become bigger, more parameters, and of course, it becomes more expensive, more electricity, so you want to learn to make them smaller. These are a few numbers about ChatGPT, right? ChatGPT uses 175 billion parameters. So if you just take 4 bytes per parameter, well, it's about 700 gigabytes, just the numbers, not taking into account memory for calculations and intermediate results and so on and so on. So how many GPUs does it take to run GPT-3? Well, you need at least 8 gigabyte NVIDIA A100 GPUs just to load the model and text. 80, what is this 80 gig? I don't understand. Probably 80, whatever. So how much data? Okay, this is interesting. So ChatGPT-3, which was released in 2020, was trained on 45 terabytes of data, right? And it has 175 billion parameters, which is about 700 gigabytes. So if you divide these numbers, so it's the ballpark is about 100 times, so maybe 50 times less, right? So the model is about 50, or yeah, about 50 times less than the data it was trained on. Okay, ChatGPT, nobody knows, but rumors are that it's not bigger than the original ChatGPT-3. And these are some different variations of the model and their sizes. They go from 125 megabytes to 175 mega million parameters to billions of parameters. Okay. I was looking for some examples where people made a smaller version of the model. Like talking about LLMs, large language models, people using BERT, which is bidirectional encoder representation from transformers, like for example, ChatGPT, using this technology. And people tried to do tiny BERT. In fact, it's on GitHub. So they made it 100 times smaller, and they got 92% of the original model's performance accuracy, which is pretty good, right? So it's not state of the art, but come on, it's 100 times smaller. There was another attempt to do like 1,000 times smaller. I found some spotty references, but not recently, so I don't know what happened to this project. Maybe it just died by itself. But they got about 75% of their original performance. And then there was another attempt called Nanobird, which is 10,000 times smaller, and got about 60% of the original performance. But 10,000 times. So you're talking going from 700 giga to, what is it, 70 mega. So it's really nothing. You can put it on hard drive of a laptop. And by the way, when the models become so much smaller, it becomes so much faster to do inference, to do predictions, to provide the output. So you really can run the model on a laptop. Methods which were used to achieve these results: knowledge distillation, layer reduction, pruning connections, weight sharing techniques, quantization of weights and activations, That's similar to reducing precision of parameters, right? So instead of using real numbers, you use just few numbers like quants. Using a neural architecture search to find smaller architectures. It's kind of similar how we was doing search in a space of hyperparameters. Huffman coding to encode weights, sparse training techniques. Okay, this is the whole area of how you create small devices which can run the models, which you can put in some, well, embedded systems, put in some devices, IoT and so on. There is a book on O'Reilly called Tiny ML. So this is example of a small device which can run a model. Okay, interesting example, of course, is Tesla. Well, in Tesla, they went all the in. They created everything their own custom. So first of all, they created their own AI chip, right? And then they created their own network architecture, which is specifically to work on this chip. So it's optimized. They all optimize to each other. They use data compression heavily. They select features, a lot of attention to that, identifying the most important features of the driving environment, focusing the model attention on them, getting a lot of training data and training, and they do training in virtual reality a lot. So this is example of onboard computer to do machine learning. It has 2 chips on it. This is example of a training facility with a new like supercomputer that they use. There are a lot of development, different brands. Of course, there is NVIDIA. Recently was a big event. It's huge. Google TPUs, well, Tesla, Facebook, Intel, Microsoft, whatever, a lot of stuff. So this is the final summary. So models can be thought of a way of compressing knowledge. Typically, the size of the model file is 1,000 times smaller than the training data. Example, GPT-3. Is it 1,000 times? No, it's about 100 times, I guess. Anyway, making models smaller, simpler, and faster becomes very important. And the last thing I want to mention is that I'm using this theme with some liquid. It actually coming from this website, Slides Go. I really like it. They have a lot of themes which you can get for free or pay for them. And yeah, I highly recommend. I recently learned how to do the themes, and I really like it. I originally was working so that Rachel can make the presentation, but she couldn't do it. So usually for myself, I'm lazy and not using the themes, but here I did. Anyway, this is it. Let me stop recording.